Hi, before today's video, I have to mention a couple things. Number one, I make PDFs of these very notes that I write during presentation. I touch them up a little bit, improve the pictures, erase some extra stuff, and then put the link in the descriptions to those PDFs. Secondly, interestingly, in HD quality, it's much easier to read my screen, even on a phone or mobile screen. And last, if you like my videos, then like them too, just to make the algorithms happy as well. And please subscribe if you have not yet. I'm almost hitting the 100 threshold. Okay, so I've written down some of the notes already to save up on time. Today we're going to talk about the surface measure on embedded C1 submanifolds of Rm. And that, yes, does require just a little bit of familiarity with manifold theory. The more you have, the better and easier this material. Okay, M is sitting in Rm always, it's n-dimensional. And with C1, I mean that the local charts are C1. Okay, you can always imagine it's a 2D space sitting in R3, and already from calculus, we know how to measure the sizes of sets. And that's how I actually motivated the area formula in my first video. Okay, but more generally, the way you define a measure on the manifold is that this is really a Riemannian manifold, by the way, by the inner product that it inherits from the Euclidean space Rm. That is why we needed it. We need it embedded already in it. So suppose you have a local chart, a local C1 chart, and you take a Borel set A living inside that image of that localization. We needed Borel so that f inverse of A is now a measurable set in Rn, and therefore we can integrate the Jacobian of derivative of fx over that set. So this mu is well defined then, and Jacobian is the same Jacobian we've been using for the area formula, and for good reasons. We saw how it's the natural quantity to consider by looking at the linear maps. And we spent one whole video justifying why Jacobian is defined this way. That was video 2. If you haven't watched, then you're welcome to do so later on. So the first lemma, as usual in Riemannian manifold stuff, is to show that this is defined independent of the local parameterization, and this is really something that depends on A. Okay, we must show that if you have A sitting also in the image of GV for a different C1 parameterization, then this quantity that we defined is independent. To do so, let's see what is the connection between these two local parameterizations. You have two copies of Rn, you have two open sets U and V living in each one of them. F goes from U, G goes from V into M. What we can do is to invert one of these, say G, and then look at the map phi equal to G inverse OF, which goes from U region into the V region. And it is C1. It's not completely obvious because F and G map into a larger dimension and then come back. But what is true is that F with this definition is just G composed with phi. So phi first goes between Rn itself, Rn to Rn, and then G goes Rn into Rm. The chain rule is holding still, so derivative of F is composition of derivative of G and phi, and by definition and easy calculation you get the chain rule for the Jacobians. So this will be our key equality here. Now we have the classical change of variables formula for integrals. We also call it U substitution, as I did here, and when we apply it to this change of variables with phi, the formula, the change of variables formula, change of variables identity, that becomes COVID, equals this. So integrating a quantity over V region here is equal to integrating the same quantity, composed of course, pulled back, in the U region, but we have to multiply into this correction determinant factor. And from the identity that is still up in the screen, that is just Jacobian of f of x. And that establishes the well-definedness of mu of A for Borel A that live inside one local parameterization. Because we can break up our manifold into countable union of pieces, each contained in the image of one local parameterization, we can extend the definition of mu to all Borel sets simply by requiring additivity. We again need to verify that it is well defined and independent of how you decompose and things like that, but that's just rudimentary stuff in manifold theory. And this measure that we've constructed is called the surface measure on the manifold. Okay, so an observation. If F is now a C1 map and 1-to-1 with a rank of derivative of F equal to n at every point, then F is a local parameterization, and therefore, by definition of mu, this star formula holds, provided with this technicality that image of F be a Borel set. Okay. Later we will see that this kind of less than desired requirement that f of a be Borel can be actually relaxed. But the main idea, the goal of this video and the next one will be to prove directly that this mu measure that we constructed coincides with the Hausdorff measure. Therefore, from the star, you can replace this mu with hn of f of a, which is now exactly what area formula gives us. And therefore, we effectively prove the area formula, except for the multiplicity function and the case of having zero derivative. I mean, zero Jacobian less than n rank, and those can be taken care of later. But the core idea is that we prove this mu equals hn. And directly, not from the area formula. We want to prove the area formula from this equality. So this is standard fact. And by being standard, that means the proof is difficult to locate in any place. It's kind of a very natural looking and intuitive thing that probably one thinks a little bit about and accepts and moves on. But I decided to give a complete proof here for the record. So let's call it a theorem. On any C1 embedded n-dimensional submanifold of Rm, we have mu of A equal to hn of A for every Borel A inside M. Borel, because mu is a priori defined only for Borel sets, but once we know this equality, then we can just say mu is defined for all sets by equating it to Hn of that set. So how do we prove this? The idea is, well, the hand-waving argument that people give always is that, okay, here's your manifold M, and here's the tangent space to it. So if you take a tiny set in M, you can approximate it by its corresponding projection on the tangent space. And the tangent space is a copy of Rn, so we know that Hn is equal to Ln. We will also take this fact for granted. I've put a video focusing on this Hn equal Ln in the playlist of area formulas, because we keep using this in area formulas. And so this is on Rn, so here it means on the tangent space. And the projection, if you take a tiny set, the projection is almost an isometry. So that the Hn of the set is almost equal to Hn of the projection of the set A. And and once you know that this is Ln of the projection, from this you can say that this is close to mu of A, because you can use this inverse of the projection as a local parameterization of A, and the mu is integral of the Jacobian of derivative of projection inverse. And this is almost equal to 1 because of being equal to an isometry, which gives you the Ln measure of the projection A. And we have shown that this is equal to Hn and to this. So ultimately you estimate mu A with Hn of A. And the proof I'm going to give is more or less the same idea, but with precise details. Okay, so to take things slowly, I break this down into a lemma first. And the lemma reads as follows. Under above assumptions, on M, fix any lambda bigger than 1. Then, for every point in the manifold, there exists a local C1 parameterization of a neighborhood of P. So there is some f going from an open subset of U into M such that, okay, for every x and y from this U, the following hold. Number one is that derivative of f of x is almost the identity map. And that is expected from isometry. So how do we quantify that a matrix is very close to the identity matrix? We can say that the dfx of v is bounded by lambda times length of v, so that would be the identity times v, and more than lambda inverse v. So for every v in Rn. So derivative, let me draw a picture of this parameter. So here's U living in Rn, and we have the map going into the manifold. So at every x, the derivative is kind of an isometry. It takes every v vector to a vector of comparable length. Part B, this is saying that f is almost an isometry. So distance of f of y from f of x in Rm, so this is like distance Rm, the norm Rm, is comparable to just distance of x and y in the domain we started with. And C, so when this is saying that f is an isometry, almost an isometry, with the metric that comes from the Euclidean Rm. So here is some point, here is another. The distance between these two, in this distance, is just regard them as points living in Rm and forget about the manifold. But we could also talk about the intrinsic distance of these 2 points via geodesics within the manifold. So that the red distance is the length of the shortest curve within the manifold that connects them. And that gives a new metric structure to M, and the Hn with respect to that will be different. But what we have is that actually, even with that distance, f is again almost an isometry. That distance we call dm, the intrinsic distance in M of f of x and f of y. Okay, so this is the red distance. Let me write down a couple of things that I mentioned quickly, probably too quickly. So M has 2 metric structures on it. As a metric space, we can talk about 2 different metric space structures. Okay, number 1 is the induced Euclidean distance from Rm, that is distance of P from Q, is just take their difference and take their Euclidean norm of that. The other is to equip M with the induced dot product from Rm, that is, we make it a Riemannian manifold with this metric. So here this metric means Riemannian metric, and take the geodesic distance on M. So dm of PQ now is infimum of length of gamma. Gamma joins a path that joins P to Q. Piecewise, say C1, or just C1. In all of this, we assume M is connected, a connected submanifold. Because if it's disconnected, then it has 2 pieces and you cannot really connect with a geodesic. But all these technicalities aside, the key lemma is, as you see on the screen, that with either of these metrics, any neighborhood, a neighborhood of any point can be parameterized by function f that is close to being an isometry, parts B and C. And part A is actually probably a consequence of B, and that is saying that the derivative is just near to being an isometry. It's not really identity map because it's between different dimensions. It's more like an orthogonal map. Okay. The proof. Okay, proof of lemma. So let's look at the proof of this lemma. And we will then see how lemma gives easily a proof of the equality of surface measure and the Hausdorff measure. Okay, I already drew a picture of how we will think about this as parameterizing a neighborhood of P from the tangent space at P, which is a copy of Rn. To make this precise though, I have some algebraic computations that are actually easier than even looking at geometry. So geometry visually is pleasing and it immediately gives you what's going on. But in this example that I'm giving you, the algebra works out even more easily. So it's not as difficult to write these down as it may look. Okay, so first we fix epsilon positive such that we've seen this before. So lambda inverse, which is less than 1, you add epsilon and still is less than 1. And then lambda, which is bigger than 1, you subtract epsilon and you're still safe. Okay, then fix P in your manifold. Then we want to parameterize the neighborhood of that and let G from some open subset of Rn into M be any local C1 parameterization. Okay. So without loss of generality, after some translations and rotations with orthogonal maps, so you don't change any geometry, any distance or whatever, we can arrange that the origin is in this V, and G maps this Z to P, which is again equal to Z, and that derivative of G applied to all of Rn, which gives us the tangent space at P is Rn times 0, which is living inside Rm. So if you have a one-dimensional manifold living in R3, this is like saying that translate it that point P to the origin and then rotate your manifold around so that the tangent to that curve is exactly the x-axis. And this can always be done, even in higher dimensions. We know that dg at 0 is injective because that's a local parameterizations and that's one of the requirements. So there exists a linear map from Rn into Rn, which is invertible, such that, so we know that derivative of g at 0 takes every point into Rn times 0. So it has 0 part and then there's the, so the n-dimensional part. So this is Rn times 0. So we can, so this basically captures the invertible part of derivative of g. It discards the extra dimension in the target, and now we can talk about basically the inverse of the map dg0. Okay, set u to be L of v. And this is not one vector, L of the open set v. This is an open set. Open image under an invertible linear map is open. And we can imagine that this is in fact living in the tangent space. So this is really, you start with MP, and then there was this there was this V region in the map G. We found the L, the invertible map, which is basically just G, derivative of G at 0. And U now is some open set living in this. Algebraically, with this notation, it is not really something in the tangent space of M, but you can imagine it is, and that explains some of the properties that we will deduce for this U. Okay, and also we see that 0 belongs to U. That's just because L of 0 is 0. Okay, now comes some of the key estimates toward the conclusion of our lemma. X going to derivative of f of x is continuous. And in many norms, including in operator norm. So, forgot to mention actually, why did this disappear? Okay. Okay, now we had this local parameterization G. G is of course doesn't have to have the properties we want. So the parameterization that the local parameterization of a neighborhood of P that we will prove has the desired properties is this one. So F goes from this open set U into Rm, which is actually it in fact goes into the manifold, and f of x is, okay, x is in U, L inverse of x brings it into V, and then G is defined on that. So this will be it. We're gonna prove that this local parameterization, this F, will have the properties we want after we make this U smaller, if needed. So first of all, x to derivative of x is continuous in the operator norm, and derivative of f at 0 is derivative of g at 0 composed with L inverse, because derivative of a linear map is itself, and that becomes the identity map. So it becomes identity and the 0 map. In other words, df0 applied to V is V and 0. So that this becomes in the tangent space 2M. Again, this trick of making the second coordinate 0 has allowed us to basically talk about Rn to Rn. Okay, the map F, derivative of f at 0 is the identity map, effectively, and the function x going to dfx is continuous in the operator norm. So, by making U smaller, well, that's ambiguous. What does it mean? On an open neighborhood of the 0, x equals 0, we will have that d of f of x minus df at 0 in operator distance is less than or equal to epsilon for every x in U. again, we call this open neighborhood U. So we will keep changing U over the calculations, but every time we still call it a U. So we discard with some part of our open set, but all of these would contain that origin 0. So this is just by continuity. So the derivative at x is close to derivative at 0, simply by continuity of df. So then what follows is that for every x in U and for every vector Rn, dfx applied to V is less than df0 applied to V plus df of x V minus df of 0 V. That's just triangle inequality. And this df0 at V, remember, is just V0, and its norm is just norm of V. And this one will become less than epsilon times norm of V because of the condition on the operator norm. But this is just 1 plus epsilon times norm of V, and that is by choice of epsilon less than lambda times V. And that is one part of the first property we wanted for this local parameterization. We get the reverse one, that this is less than df of x at V analogously. And by that I really mean it. Just reverse, do different triangle inequality. Okay, so that gives us the first property, that derivative at every point in that neighborhood is almost like an isometric linear map, an orthogonal map. Okay. To continue, we reduce first to a convex open set U. Okay, we can even take just a round perfect ball in Rn. And the reason for that is that I want the straight lines to be within my set. Okay, what you get is then, given now x and y inside your U, let gamma t parameterize the line segment in the obvious way. No crazy parameterization, just constant speed. And we parameterize it from 0 to 1. So over the interval 0, 1. Gamma of 0 is x and gamma of 1 is y. Then, okay, let's look at, so first of all, the distance in the Euclidean. Okay, we had two metric structures. Let's first look at this one. F of x, y minus x, and this is always less than or equal to the intrinsic distance of f of y and f of x, because the shortest line, the shortest geodesic between fx and fy is this straight line, and it may or may not be within the manifold. So if you insist on being the manifold, you may have to take a different path, which only makes it longer. And but so if we show that this dm is less than something, we have already shown that the other metric is also less than that. By definition of the dm, notice that FO gamma is a curve, is a C1 curve that connects f of y to f of x. So the length of this curve is more than the dm, because dm is the infimum of all such length. So how do you compute length of the curve FO gamma? You take derivative of this curve, you take its norm, and then you just compute it at t dt from 0 to 1. And this by chain rule is derivative of f computed at gamma t dot gamma prime of t. That's a matrix times a vector, and then you take norm dt. But this is less than 0 to 1, operator norm of df at gamma t, norm of gamma prime of t dt. And this becomes less than or equal to the operator norm of, so gamma t is a point in U, so its operator norm is less than 1 plus difference of operator norm of that minus df at 0, and that was less than epsilon. So by being close to the df at 0, we have this estimate, and this is gamma prime of t dt, and that gives you 1 plus epsilon. Gamma prime joins x to y. I mean, gamma joins x to y, so its integral of gamma prime is just length of that line. And that is nothing other than x minus y. And this is less than lambda x minus y. Okay, let's see what we have proven. We have proven that this thing is less than that for every x and y in the domain of parameterization, and also we've shown this is less than that, and this was 1/2 of the second and third properties that we require from this local parameterization. Then again, from the fact that dm distance is larger than the Euclidean distance, all we need to show is that even the smaller of these, so it remains to show that for every x in U, for every y in U, f of x minus f of y, this is the Rm distance, is bigger than or equal to lambda inverse x minus y. If I show that, then we know that this is less than dm f of x f of y, and I will have completed the other halves of the second and third properties I wanted for this. And this follows from some other quite satisfying calculations. So I've given this some thinking, and once everything works out perfectly, you know, that feeling when all calculations just come together. Okay, for given x and y, just define these two vectors. So let alpha be f of y minus f of x. That's a vector in Rm. And beta to be derivative of f at 0 applied to y minus x, which we know is just y minus x comma 0. But we want to keep it in this form intentionally. So observe then that alpha is integral from 0 to 1 of, this is fundamental theorem of calculus applied to the line segment from x to y. So this will be d of f. This is the parameterization of the line from x to y. So x plus ty. This is the convex parameterization, and y minus x. This is the dt. Okay, so this fundamental theorem of calculus applied to the function f of 1 minus t x plus ty. This function from 0 to 1 into Rm. If you apply the fundamental theorem of calculus, you end up with this identity. On the other hand, beta is integral from 0 to 1 of df at 0 y minus x. And this is nothing fundamental because I'm integrating a constant vector over an interval of length 1, and this is just always true. So from these two then, let me compare the norms of these two guys. I mean, let me compute the distance of these two. So from the integrals above, this is integral from 0 to 1 of derivative of f at a point along the curve x, ty, times y minus x, but I want to factor that out. So df at 0 now times this matrix times y minus x, dt norm. What is true is that if you take the norm inside an integral, you get a larger quantity, so 0 to 1. And now, norm of this matrix applied to y minus x will be less than the operator norm times the norm of y minus x dt. And this is operator norm of df 1 minus tx plus ty minus df at 0. But guess what? This is a point in my u, and this is 0. And from the very first things that we arranged was that the operator norm doesn't change more than epsilon within that neighborhood. So y minus x dt, and this is just a constant thing being integrated, and that's it. Okay, why did I do this calculation is because I wanted to estimate from below this quantity, but this quantity is just my alpha, and now by triangle inequality, this is beta minus alpha minus beta. Okay, and this will become norm of beta is equal to just norm of x minus y, because beta is just a vector x minus y comma 0. And what is the biggest that alpha minus b norm can subtract? That is this calculation. The most it can subtract is minus epsilon x minus y. But this is 1 minus epsilon, norm of x minus y, and that is bigger than lambda inverse x minus y. And this was all that we wanted. Now this is the other direction of property 2, and because dm is bigger than this one, also gives a lower bound in property 3 that we wanted. And therefore, everything is completed. So this was quite long, so let me recall what we just proved without scrolling back up. Given a manifold at every p, we have a local parameterization of a neighborhood of that point such that f of y minus f of x distance is between lambda x minus y and lambda inverse x minus y, and similar property holds with the other distance. And furthermore, we have that derivative at x, any point of this u. Okay, f of x, f of u somewhere here and here is almost like an orthogonal map. Okay, now proof of the theorem we wanted. The theorem that mu, this surface measure that we have constructed and defined, is the same as hn. And this will be amazingly not much longer, thanks to this beautiful lemma that we have just proved. Okay, given lambda bigger than 1, we cover a given Borel with a countable, at most countable, maybe finite limini, union of AIs such that, so we write A as union of AI such that AI are also Borel. For each I, there exists some parameterization from some open set that satisfies the assumptions of the lemma. That means, by the way, that lemma, I call it almost isometric local parameterizations. And of course, this if I has something to do with f, AI has to do with fi. Okay, fi, AI is in the image of this local parameterization. And that's it. So pictures never hurt. Here is your A, and then you cover it by pieces, disjoint. You can always remove the overlap. And now every piece, say this one, is one AI. And it's contained in the image of one local parameterization that is an almost isometry like this. Okay, now what we have is that Hn of AI, okay, is less than or equal to lambda to power n Hn of f inverse of AI. Why? Because f is lambda by Lipschitz. And this is a universal fact about Hausdorff measure and how it behaves under by Lipschitz maps, or simply Lipschitz maps. And now we use the key lemma that on Rn, Hn is equal to Ln. And that tells me that this is Ln of f inverse of fi. I know this is a measurable set also because AI is Borel. And this equals lambda n, writing it in more complicated ways. So I just integrate the constant function of 1 over the set f inverse AI. But for good reasons, as soon you will see. From this fact that df of x here is between this and that, we can easily show that the Jacobian of dfx is bounded by lambda n and bigger than lambda to power n. Just by, for example, looking at eigenvalues of the matrix, like polar decomposition gives this, and also you can look at how big the image of the unit ball can be. So the image of unit ball will be contained in a ball of radius lambda, and it will contain a ball of radius lambda inverse. So, but anyhow, this is an easy calculation to do. So we can continue our calculations above. The last thing we computed there was that this is lambda n f inverse of ai integrate 1 over this set. So now this will become, I can replace this by lambda 2n integral f inverse ai of Jacobian df at x d ln of x. Yeah, so I replaced 1 by lambda to power n Jacobian dfx, thanks to the last inequality that we had. Okay, so I have this less than that, and this less than the one there. So putting these together, I have proven that Hn of ai is less than or equal to lambda to power 2n, but do you recognize this quantity? This is by very definition just mu of ai. So we did this for one ai, so do summation over I to get that Hn of the Borel set is less than or equal to lambda 2n mu of a. Similar calculations, and I mean similar calculations, give Hn of a is also bigger than lambda to negative 2n mu of a. What you do then, because lambda is arbitrary, let lambda descend down to 1 to get that Hn of a equals mu of a. And that's the end of the proof of the lemma. I did not include the calculations for the Hn, so exact same proof also proves, we already had it inside the lemma. In the lemma we proved that the local parameterization is an almost isometry with respect to either distance, the intrinsic distance or the induced Euclidean distance. That Hn, this Hausdorff measure, computed with respect to this inner metric, also coincides with the mu. Exact same proof as above, just change Hns to Hndms, and every estimate we had there is still true there. And an interesting thing here is that although you do get this from the area formula, once you know this is integral of Jacobian, like from the other proof, and by definition this is integral of Jacobian, so these are equal, then therefore these are equal. You do get this from the area formula, but I'm not sure how you can get this other one from the area formula. So I think you will have to do some local isometric parameterization anyway, or you have to prove that on a very tiny scale on the manifold, the distance, Euclidean distance, and the intrinsic distance are almost isometric. Anyhow, we have this theorem now, and let me actually go then. We had a statement of a theorem, and then we proved something more. So we have a proof. Then let's also write the theorem. So we can include that this is equal to hn computed with respect to the other distance. And this is the key lemma, the key result that we will borrow from this video in the next video to give a proof of the area formula. Again, the idea is that now that we know hn equals to mu, and we know that mu by definition is just integral of Jacobian, we get the area formula for C1, 1-to-1, and full rank functions. But we will do the adjustments so that we capture the multiplicity function, and we will apply the Sard's theorem to also capture the low rank part. So a second proof of the area formula using this in my next video. Sometimes once I finish the videos, I realized that there were some key points that I did not emphasize enough, but so let's walk backward and see how all of this started. So in summary, you see that all of this boils down to this amazing change of variables formula, this U substitution formula. Because we have this U substitution, we have that the surface measure is well defined, and we can then say that even the area formula is a consequence of this U substitution for integrals. I hope you have enjoyed this video, and the amount of details was remarkable, I have to admit, and but that's how it should be sometimes. Some arguments are everywhere, everyone gives the same sketch, but at some point we need also proofs. Thanks a lot, and see you in my next video.